Welcome everyone to Bileşik Algebra and Number Theory Seminar. Our next speaker is Professor Andrej Dujella from University of Zagreb, Croatia, and he will talk about Diophantine m-tuples and elliptic curves. Thank you.
Thank you very much. It's my great pleasure to have opportunity to give this talk. I would like to thank Professor Ilker Inam and members of Bileşik Algebra Number Theory Group for their kind invitation. In my talk, I will, as the title says, speak about two subjects, Diophantine m-tuples and elliptic curves. In fact, these two subjects were my favorite research topics in past years. So I would like to discuss connection between these two notions, and we will see that these connections goes to both directions. Namely, elliptic curves can be used to solve some long-standing problems concerning Diophantine m-tuples, but also Diophantine m-tuples can be used as a useful tool in producing elliptic curves with interesting Mordell-Weil groups. So I will start with the Diophantine m-tuples and a little bit of history. And everything started with Diophantus of Alexandria in the fourth part of his book of arithmetics. He asked the following problem: find four numbers such that product any two of them increased by one is a perfect square. And for him, numbers usually meant positive rational numbers, and his solution was of that shape, so he found four positive rationals with a given property. Later, Fermat became interested in several problems studied by Diophantus, and in particular in this particular one, and he was able to find solution in positive integers. So the set 1, 3, 8, and 120 have this property of Diophantus. As you can see, if you take any two of two distinct elements of this set, multiply them, increase by one, you will get a square. So here we have these six conditions satisfied. And these examples motivate the following definition. Set of m non-zero integers is called Diophantine m-tuple if product any two of its distinct elements increased by one is a perfect square. If elements of such sets are non-zero rationals, then we call such set a rational Diophantine m-tuple. And the principal main question in this subject is how large such sets can be. In fact, here are two quite different questions, namely how large such set can be in integers and how large such set can be in rationals. So questions are different. Our knowledge about these questions is different and answers are different. So let me start briefly by mentioning what is known in integers. So we saw one example of a quadruple found by Fermat. Euler was able to prove that there are infinitely many Diophantine quadruples. His result was more general, but here even this is enough to somehow show that this statement is true. So this set of four elements has a property of Diophantus for any k greater or equal to. In opposite direction, first important result was due to Alan Baker and Harold Davenport in 1969. They proved if we start with 1, 3, and 8, this subset of set of Fermat, then fourth element has to be 120. In particular, Fermat sets cannot be extended to integer quintuple. And this result motivated conjecture that there is no integer Diophantine quintuple. In 2004, I was able to prove that there are no sextuples and there are only finitely many quintuples. Finally, in 2019, He, Togbe, and Ziegler proved that there does not exist a Diophantine quintuple. So in some sense, problem in integers is solved. However, there are still interesting open problems in this area, namely motivated by the result of mentioned result of Baker and Davenport. As I said, we may rephrase this result by saying that Fermat quadruple cannot be extended to quintuple. But in fact, this result is more specific, stronger. It says that if we fix 1, 3, and 8, then fourth element is unique. So we may ask, is it true in general that if we fix A, B, C, then D is fixed? So first we should say what is 120 in general situation, and Arkin, Hogarth, and Strauss provide the answer. So if we start with the triple ABC, which is good, product plus 1 is square, then we can define quantities which I denote by D plus and D minus, and it is easy to show that ABC can be extended to quadruple by D plus, and also by D minus if D minus is not 0. So in case of 1, 3, 8, D plus is 120 and D minus is 0. So in that particular case, extension was unique. But in general, we may have at least these two extensions. And conjecture, which is still open, is that there are no other possibilities. So if we have a quadruple, then fourth element is either D plus or D minus, which can be written in this more symmetric way, and such quadruples are called regular. So conjecture is that all quadruples are regular. As I said, it is still open, but something is known. For example, in joint work with Attila Pete in 1998, we proved that all quadruples containing pair 1, 3 are regular, which is quite generalized by Fujita, and one particular case result joint work with Yann Bijot and Maurice Mignot was needed. So result is that all quadruples containing pair K minus 1, K plus 1 are regular. But conjecture is open, so what is the best known result in that direction? So if we start with triple, in how many ways it can be extended to quadruple with larger element? And the best result at the moment is that there are at most 8 ways. This is a result due to Chipu, Fujita, and Miyazaki. In opposite direction, so if we start with A, B, C, so this is a result by extended by larger elements. So if we ask in how many ways we can extend it with the smallest element, then in joint work with Michai Chipu and Yasutsugu Fujita, we prove that there are at most 2 ways. But so here still some open problems remained. Let me now switch to rational case where situation is quite different. We don't know any upper bound for the size of rational Diophantine tuples. It is even not clear what to conjecture, what should be conjectured here. So let me say what is known. First important result is due to Euler. He proved that there are infinitely many rational Diophantine quintuples. In particular, he was able to extend Fermat sets 138 and 120 by fifth positive rational number. This result was generalized by Arkin, Hogarth, and Strauss, and they proved that any triple can be extended to quintuple. And in 1997, I generalized it further and proved that all Diophantine quadruples satisfying some technical requirement can be extended to quintuple. And what is important for the remaining part of my talk is that my construction gives, in principle, two different extensions. Unless quadruple is regular, and in previous constructions due to Euler and Archie-Hogard and Strauss, their quadruple was regular, so they have only one extension. So if we have two different extensions of quadruple to quintuple, and if we put these two extensions together, then we may hope that maybe we can get sextuple, because only one condition is missing. So you have two quintuples containing the same quadruple, then only condition missing is that if we put these two extensions together, multiply, increase by 1, we should get a perfect square. So is it possible or not? It is not clear at the first sight, because this expression are quite complicated and it is not clear what to expect. But first result, important, coming after a few centuries, that it was open question whether there exists any sextuple. Phil Gibbs in 1999 obtained several examples of Diophantine sextuples, and some of them really use this idea presented in my questions. And in 2017, in joint work with Matija Kazalicki, Miljan Mikic, and Marton Szikszai, we proved that there are infinitely many rational Diophantine sextuples. In meantime, several other constructions of Diophantine sextuples appeared, but next natural question, is there any seven-tuple, it still remains open. So we don't know almost nothing. I will say something in negative direction and something in positive direction, but without any conclusion what to expect here. So some results is say negative direction, which would suggest that perhaps there is no seven tuples. Hermann, Pette, and Zimmer in 1999 proved that if we start with quadruple, then there are only infinitely many extensions to quintuple. Results is very interesting, but ineffective because it uses Falting's theorem. So they assign to this question a curve with genus 4 and then conclude that there are only finitely many rational points on this curve. This approach also gives some idea why should we have some absolute upper bound for the size of rational Diophantine tuples, because length conjecture of varieties of general type implies that if we have a curve of genus greater than 2, there should be some upper bound for the number of rational points. More concretely, so these are ineffective results of conjectures, but some very concrete result also solving open problems from time of Euler. As I said, Euler proved that if we start with with 1, 3, 8, and 120, then we can extend it, this Fermat sets, by following rational number, but the question remained whether this extension is unique or not. And Michael Stoll in 2019 proved that, in fact, this extension is unique. So I show us that looking just on this slide, one might expect that there are no seven tuples, but also perhaps that there are no six tuples. But we already saw that there are six tuples. So this is not end of story. So some results in opposite direction. I already mentioned that we know that there are infinitely many sextuples, but even more. We know that there are infinitely many triples, each of which can be extended to sextuples in infinitely many ways. So there are really many, many sextuples, which suggest that perhaps seven tuples is possible. Moreover, in joint work with Matija Kazalicki and Vinko Petricevic, we presented some alternative construction of sextuples, and in particular, we show that there are infinitely many sextuples satisfying some additional properties, like presented here. So if we want that all denominators are squares, there are infinitely many examples of that shape. But maybe the closest that we can come to seven tuples are something called almost m-tuples. So due to Gibbs, Kazalicki, and Petricevic, now we know almost 100 examples of almost seven tuples. What it means almost seven tuples means seventh number when only one condition is missing to be a rational seven tuple. For example, these five numbers together with these two gives seven numbers when only one condition is missing. So only missing condition is that this product plus one is not square. All other conditions are satisfied. There are some other, say, positive results in sense that we show that Stoll proved that this particular quadruple has unique extensions to quintuple. And we know in general that they may be two extensions. But in fact, there are examples which much more. Extensions, for example, this quadruple can be extended to quintuple in at least 6 ways. And there are also examples of quadruples which can be extended to sextuples in many ways. So I will stop here about Diophantine tuples with rational Diophantine tuples without any conclusion what to expect about seven tuples. So the next notion from the title of my talk are elliptic curves. So they can be defined over any field as a non-singular projective cubic curve with at least one k rational point, but using birational transformation, it can be always transformed in this so-called Weierstrass form, and I will not consider a more complicated equation of elliptic curves in my talk. In fact, since I am mostly interested in elliptic curve over rationals, namely over field of characteristic 0, then elliptic curve can be further simplified in this what is called short Weierstrass form. And then non-singularity means that this cubic polynomial has no multiple roots, or equivalently that discriminant is non-zero. And one of the most important facts about elliptic curves is that a set of k-rational points forms an abelian group in, say, natural way. This natural way can be visualized if we assume for the moment that underlying field is field of real numbers, so that we can draw some picture. So elliptic curve can look like this or like this. And to add 2 points, we draw a straight line through these 2 points, and because elliptic curve is a curve of degree 3, we can expect that this line intersect a curve in one additional point, and opposite point of this intersection is defined as P plus Q. And similarly, if we want to add a point to itself, then we draw tangent line through given point, and again we may expect that in general situation this tangent line intersect curve in one additional point, and opposite point is defined as P plus P or 2P, and it can be shown that this gives addition which satisfy conditions of abelian group, not only over reals but over any field. And as I already mentioned, I will be mostly interested on elliptic curves over rationals. And what is very important as somehow starting point for me is famous Mordell-Weil theorem, which says the group of rational points on an elliptic curve is finitely generated abelian group, which means that this group has this shape. It is product of torsion group, namely a group of points of finite order and finitely many copies of infinite cyclic group. So this group is called torsion group, and this quantity here is called rank. So it is very important result, but we would like to know more. We would like to know which possible torsion groups, which groups are possible as a torsion groups, which ranks are possible. And perhaps the most ambitious question would be to say which combination of torsion groups and ranks are possible. And this is a question in which I became interested and which is somewhat connected to Diophantine tuples. So what is known? Answer is known only for the first question, namely what torsion groups are possible. By Mazur theorem, we know that there are exactly 15 possibilities. There are 11 possibilities of this cyclic shape and 4 possibilities of this product of 2 cyclic groups shape. Concerning rank, it is not known what values of rank are possible. For a long time, it was conjectured that there exists elliptic curves with arbitrary high rank. And even if we fix torsion group, any of these 15, torsion group, that rank can be arbitrarily large. However, there are also some recent heuristic arguments suggesting possible boldness of the rank of elliptic curves. In particular, one very popular, which I will come to it later, predicts that there are only finitely many elliptic curves with rank greater than 21. If this is true, then certainly rank will be bounded. So what is known? It is known that there exists an elliptic curve with rank greater or equal to 28. In fact, equal 28 if we assume some usual assumed conjectures. This was found quite recently by Noam Elkies and Zev Klasbrun in 2024. And here you can see that there was some, say, big gap in discoveries. So for a long time, a record was 28, and then a year and a half ago, a record was broken by Elkies and Klasburn to 29. So again, it is hard to predict what is true answer. As a curiosity, I could mention that Elkios soon after this discovery informed me of this result, because I maintained several on my web page several tables with records of ranks. I will show some other tables later, and then I announced their result on Twitter, and in few days I got to 100,000 views. So no one of my announcements never came any close to this number. So probably it is the most popular announcement in which I was involved, and probably it will stay like that. Okay, so I said something about Diophantine tuples and something about elliptic curves. Now the main subject, a connection between these two notions. So how they are connected? So if we start with the triple, say rational Diophantine triple, it is natural question how to extend it to quadruple. If we call this fourth number x, then we have this free condition which should be satisfied. If we multiply these three conditions, then we get one condition of this form. So we have square and cubic polynomial with different roots, namely we have an elliptic curve. So this gives a principal connection between Diophantine triples and elliptic curves. What can be said about this curve, why it might be interesting and important? So first, we can see some obvious points on this curve. 3 points of order 2, namely corresponding to roots of this cubic polynomial. So we have 3 linear factors, and each root produce curve of point of order 2. But there are also, say, more interesting points, which in general could be of infinite order, namely point with first coordinate 0. So if we insert 0 here, here, and here, we will get 1, which is square. So point 0, 1 is always on this curve. But also with some more work, we can see that if we insert for x1 over abc, then in the numerator we get a square, a square, b square, c square, and in the denominator and in the numerator we get ab plus 1, ac plus 1, bc plus 1, which is square by definition of Diophantine triples. So in general, we have these 2 additional points, and these both points are interesting. We will see soon one and the other reason. So first point P is important because it answers the natural question. What is connection between 3 and 4? So if we have 3 squares and multiply them, certainly we get a square. But how about opposite direction? Certainly in general it should not be true. So we can have numbers 2, 3, and 6 and multiply them, we will get square, but no one of them is a square. So question is, can we characterize points here which satisfy this stronger condition? And the answer is that it is enough to have 1 point which is good, and point 0, 1 is good. So if we put 0, we have 1, 1, 1. 1, 1, 1, we have 3 squares. So we have 1 point which is good, and all others can be obtained by this rule. So if we add to this point P any point of the shape 2 times something, so any double point, we will get a point which satisfy initial condition. And so what is important about point S? S is exactly of this shape. So it is not immediately clear or obvious, but it can be easily checked that S is of the form V plus V, so double V, where V is this point. Which means that if we start with point T, which is good, then also points T plus 1 and T minus 1 are good. So this was all obvious or follow from some known facts on elliptic curves. But what might be a little surprise is that if we put together T and T plus S, or T and T minus S, they are good to be put together. So product plus 1 is always a square. This is just a modern language interpretation of this previous result, which was obtained in the style of Euler, namely these quantities E and F, which I presented before as some complicated formulas without any explanation how they can be obtained, are just other interpretation of this result. This result has important generalizations, and this is, say, one of the main ingredients on joint work with Kazalicki, Mikic, and Szikszai. Namely, we ask the following question. So we take T and T times plus something. So in previous slide here we have S. So let me play S, but any other points. We would like to have something similar. But we cannot expect that in general, but any point we will have product plus 1 is a square. But can we have anything similar like that? And it appeared with very simple proof, few lines prove that this is true if we allow some additional, say, cofactor. So if we are willing to allow the third factor, then some general result of this form is valid. And now we can first explain this previous result. So what is also special with point S? So point S has a first coordinate 1 over ABC. But this was for the shape of curve written here, which is not in Weierstrass form. In particular, this polynomial is not monic. It has first coefficient ABC. So if we get rid of this coefficient, but this standard method, our first coordinate will be multiplied by the ABC. So only number 1 will appear here, which means that this cofactor, if we take point S here, we became number 1, and we will have a result product plus something is square, what we needed. But this is not just to explain a previous result, it is to obtain new result. Namely, consider now this structure, this 6 elements. We started with some ABC, then we have point T, which is good. We have points T minus S and T plus S, which are good. But question is it really a sextuple? And from what we know, there is only one missing condition. So everything is satisfied, except there is no reason that these two put together are good. This was written before in this shape, E times F plus 1, is it square or not? Now we have written it in different shape, but it is the same condition. But now we know that this is almost satisfied. It is satisfied if we allow to put something here as cofactor. What is cofactor? It is different between these two quantities. So T plus S and T minus S meanings we have cofactor first coordinate of 2S. And we would like this to vanish as before. And first idea would be, okay, if 2S is equal S, then it will vanish the same as before. But 2S is certainly not S. So in any group, we know what does it mean. It means that S is a neutral element. So it is not true. But what is important, one important property of elliptic curves is that point S and point minus S has the same first coordinate. Just they differ in the second coordinate. So if we are interested only in first coordinate, then 2S equal minus S is equally good for us. And 2S equal minus S meaning 3S equal 0, which means that we want that point S is of order 3. And now we already came close to arithmetic of elliptic curves because we already have 2 points of order 2. So we have points of order 2, and now we would like to have 1 point of order 3. And by Mazur theorem, there is only one possibility. So this might be possible if we can obtain torsion group Z2 times Z6. And we were able to write everything explicitly. I will skip, I will not discuss this condition, but certainly it is something symmetric. And if we insert elementary symmetric polynomials, then everything simplifies. And we were able to find parametric solution of this previous problem, namely ABC, given as a function of one parameter, satisfying condition that 3S is 0. What we obtained what I claimed, infinitely many triples, each of which can be extended to sextuple in infinitely many ways. To be, say, specific, although not very nice result to present on this talk, let's take 1 point which is good. So this T should be P plus 2 times something. So the simple solution will be to take p plus 2 times p. So take 3p, then 3p plus s and 3p minus s are certainly good. And we have sextuple, and it does not look very nice, but it gives a parametric family of sextuples. Later, we found some simpler families with different methods, but I don't have, I think, time to present other constructions. But this shows how elliptic curves are used to solve problem which was open from time of Euler. If we are interested, say, in style of Diophantus, he existed in positive elements. So our rational functions certainly are not always positive, but we can choose elements in some intervals to produce all elements with positive coordinates. Like, for example, if we take t equals 6, we get these 6 positive elements. And now the opposite direction. So how Diophantine triples can be used to obtain something interesting in the field of elliptic curves. In particular, in the questions which I, perhaps only important question which I mentioned concerning elliptic curves, and this is what combination of torsion and rank are possible. So let's come back to elliptic curves induced by triple, and we may ask which torsion groups can appear here at the first, and then we will ask which ranks are possible. By Mazur theorem, since we have 3 points of order 2, by Mazur theorem, in Mazur theorem there were 2 lines, 2 rows. Only the second row can appear, so we cannot have a cyclic group if we have 3 points of order 2. So in principle, these 4 possibilities can appear. But again, whether they really appear or not, it depends whether we consider integers or rationals. In an integer case, in the joint work with Mille and Mikic, we were able to show that m equal 2 and m equal 4 are not possible. And at the end, I will mention some open problems, and one of them is whether m equal 3 is possible or not. So one may speculate, perhaps conjecture will be too ambitious, but one may speculate that only m equal 1 is possible if we consider integers. But in a rational case, which is in this context much more interesting, all groups can appear, and all of them give some interesting results. Namely, interesting if we consider a combination of torsion group and rank. So, starting point are our parametric formulas of rational sextuples. They look so awful that one is perhaps surprised that they have application, but indeed they have. So we will choose different subtriples. For example, for simplicity, let's look last 3 elements, and then we will look at the first 3 elements. If we look at the last 3 elements, then we consider this elliptic curve. We know from before that we have points which correspond to point P and to point S. So these 2 points are always present, and we may expect that they are of infinite order and independent. There is no obvious reason why this should not be hold, so we may expect that this is true. But here we have 3 additional points, because this is sextuple. Also A satisfies this equation, and B satisfies this equation, and C satisfies this equation. So we almost for free, we obtain 5 points, which looks like independent points of infinite order. And there are tools how to prove it. And in fact, there are 5 points of infinite order, showing that there are elliptic curves over Q of t with torsion at least Z2 times Z2 and rank at least 5. It is not far from a current record for such curves, but enjoyed work with Julian Aguirre and Juan Carlos Peral. We were able to improve this 5 to 6 and also to find specific curves which quite larger rank, namely rank 12 over Q. I will near the end say something about methods, but let me now choose first triple, ABC. It looks like a bad choice. Why? Because S here is not on infinite order. In this case, S is of order 3 by construction. Also, this ABC. Now these additional points are D, E, and F. And all these points, D, E, and F, are obtained as some combination of points of P and S. So they are certainly dependent. So altogether, we don't have nothing better than rank 1. But in our favor, it goes that point S is of order 3, which means that we have this quite strange, in some sense, not the usual torsion group, quite large, almost largest possible torsion group, and perhaps surprisingly, even this simple result is quite near to the record. And with some more efforts, we were able to increase this rank 1 to rank 2, which is indeed a record. And we were able to find examples of rank 6 for this torsion, which is indeed record. And corresponding, one of corresponding triples is written here. So these simple ideas were able to come to current records. But in one category, we were able to break all records at that time, namely for curves of the with torsion group Z2 times Z4. Perhaps I should be a little faster to give time for questions and open problems. So I will give only conclusion. So we were able to prove that there are curves over Q of T with rank 4, and there are examples over Q with rank 9, and in both cases this break record at that time, and still these are current records for this torsion group. Here, in fact, we were able to prove the rank exactly 4 over Q of T using algorithm due to our colleagues Ivica Gusic and Petra Tadic. And finally, the last torsion group possible is Z2 times Z4. And here is interesting result that all elliptic curves of that shape of the torsion groups can be induced by Diophantine triples. So in particular, current record for such curves, which is only 3, and I will discuss this at the very end, comes for Diophantine triples. So to summarize, this is one of the tables from my web page, current record for the rank with given torsion group. Here you can see some familiar numbers like 29, which is current record in absolute category, and in particular it corresponds to trivial torsion, but also these 3 numbers which were already mentioned in my previous slides. These are 3 records which were obtained using Diophantine triples. And let me come to some other tables. So how to obtain such examples? I already mentioned that usually starting point is some family of elliptic curves over Q of T. And here records are certainly smaller. We have seen smaller number, but again, in 3 categories, records come from Diophantine triples. Here we are near to the record because absolute record is 7 and record corresponding to Diophantine triples is 6. And the last table is somewhat motivated by application. So I didn't plan to speak about application, but elliptic curve with large torsion have application in factorization. In Lenstra factorization method, but missing ingredient is that there is needed large torsion and positive rank. And here in this table, you can see many zeros. Zeros which usually appear in the places with large torsion. So zero and large torsion is not good. So the question is, can we somehow parameterize elliptic curves with different method, not necessarily in this form, to allow to replace 0 by 1s, and here you can see there is no zeros here. And I promised to mention heuristic. So this 21 was already mentioned, that there are only finitely many curves with rank greater than 21 is predicted by heuristic due to Park, Poonen, Voigt, and Wood. And here we see that it is known that there are infinitely many curves with rank greater or equal 19. So these numbers are close, and perhaps it suggests that heuristic might be found. But in some cases, this heuristic is so good, is too good to be true in some sense. So what these blue numbers say? That the best current result is the same as the prediction as best possible result due to heuristic. So it says that it is not possible to get better result. So for example, this free means that we know that there are infinitely many curves with rank greater or equal 3, but heuristic says that it cannot be better. So that there are only finitely many with rank greater or equal 3. But the last result before open questions is somehow problematize this blue quantities. Here I will give a few details only in this largest torsion group of that shape, namely joint work with Mattia Kazalicki and Juan Carlos Peral. I will skip details. We proved that there are infinitely many curves of this rank, of this torsion, and the rank 3. In fact, we found a rank 3 family with this torsion group, and the family is too complicated to make any computation of ranks. So we cannot say that there are many curves with rank, say, 4 in this curve, in this family. But what we can do is to compute parity. We can compute root number, which conjecturally, assuming Birch-Swinnerton direct conjecture, predicts parity. And this picture shows that so blue dots correspond to even rank, and orange correspond to odd rank. So without mentioning numbers, and numbers are written somewhere here, there is even more even than odd numbers here. So all this suggests that perhaps there are infinitely many even ranks. But even and greater than equal to 3 implies greater or equal to 4. So if this heuristic about distribution of odd and even ranks is valid, then this suggests infinitely many curves with rank greater or equal 4, where the heuristic says only finitely greater than 3. So perhaps heuristic needs some adjustments, I'm not sure. And at the very end of my talk, I promise in the abstract that I will mention some concrete open problems. Problems can be found around 60 problems can be found on my web page. Namely, recently I published a book with the same title as the title of my talk, and for each there are, I think, 5 chapters, and for each chapter I prepare 10 to 20 problems, and here I choose one problem from each chapter. Almost randomly, I certainly wanted to choose the first one and the last one. And the first one, so first problem from chapter 1, goes back to Diophantus. And I started my talk with this quadruple. And I said this is Diophantine quadruple. And I think it is very natural problem to ask how this quadruple can be extended to quintuple. And general construction gives two extensions, but is there any other possibility? It is, as far as I know, open problem, and I find it interesting, and perhaps someone might try to work on it. From the second chapter, something which I almost mentioned. So this is largest possible torsion group due to Mazur's theorem. And here I mention briefly at that point, the current record is free. So, and this is the only, if I go back to this table, it is only number 3 in this table. So in this table, number 3 appears only here. So for all other torsion groups, we know at least something better. Sometimes much better, but at least 4 is possible in all other situations. Is it possible here? I think it is also an interesting problem. As you can see here, this rank 3 was obtained by many examples, by many different authors, starting from 2000 and at the moment finishing few years ago. So I found this problem also interesting and say computational flavor. This is also a problem which I already mentioned. If we consider a Diophantine triple in integer case and we ask which torsion groups are possible, then only remaining question was whether this m equal 3 is possible, and this m equal 3 corresponds to this torsion group. So we know that it is possible for rationals, but is it possible to integers is open problem. There is no known example. There are some partial results due to Attila Pete, Philip Neumann, probably the more general due to Miljan Mikic, for some triples of, say, parametric form or a double parametric form that this torsion group is not possible. Perhaps they suggest that there is no such torsion group, but it is certainly open problem. Somewhat related problem is question related to this equation 3 and 4. So product of two squares and the elliptic curve, which is obtained by this product. So in several cases, in many cases, we know that if we start with triple, that fourth element is unique. So this particular quadruple was shown in one of my first slides. So first result by Euler was that these 4 quantities form a quadruple, and I was able to prove that if we start with this triple, fourth element has to be this one. So it means that I know how to solve problem 3 for this triple, but we don't know how to solve problem 4 in this situation. So this is, at least in principle, harder problem to find all integer points on this family of elliptic curves. So if rank is as small as possible, then answer is there are no other points. If rank is larger, but we know the reason why it is larger, we also know the answer. Philip Neumann made some, say, systematical consideration without assumption of rank. So in this range, there are no other points, but whether there is any, is it true for any k, it remained open. And my last problem and last problem on the list is chapter 5 and last problem 17 from very recent, my last paper. It is still preprint, joint work with Laszlo Szalai. So we consider triples with one additional condition. So this is condition for Diophantine triples. And we ask, is it possible to have product any 3 plus 1 is a square? And we were able to prove that there are infinitely many such triples. So we have triple, we choose 2, we choose 3. And our colleague Tomislav Pejković asked, what if we choose 1? So we can choose 2, we can choose 3, but we can choose also 1 element. So what if we add these 3 additional conditions? It is very likely that there are no integer solutions of this additional condition, but in rationals there are solutions. I found some of them. Later, my colleagues Matija Kazalicki and Vinko Petricevic find more such examples, but still it is open whether there are infinitely many such triples, and I find this problem also interesting. And I'm at the end of my talk. Thank you very much for your attention.
Thank you very much for this interesting talk and then fruitful open problems. Are there any questions or remarks? Actually, I have one question, a little bit long. Maybe it makes no sense. Sorry, but it's an experimental question of mine. During my PhD studies many years ago, I compute some orders of Selmer groups of elliptic curves in twist families. And due to my experience, due to my experiments, I find some families of elliptic curves which all rank 1, for instance. Due to Walsh-Bourget theorem, we have some congruence classes in some special conditions, and in some classes, if first in this theorem we fixed an elliptic curve to twist, and then we have some twist factors coming from these congruence classes, and mostly I have rank 0 cases, but in some special examples, actually I have also some data on it. I have some families of elliptic curves which all seems rank 1. Actually, I have one example with higher rank, but I have it seems that we have a stable regular 1 case. Is it worth to work on it?
I think yes. So it is not directly related to what I worked, but it sounds interesting. So I cannot say immediately any reason why the answer should be obvious or something like that. So it might be interesting to work on it, but I cannot say much, fortunately.
I see. It seems that there may be some connection with the congruences coming from Walsh-Bourget theorem and then the ranks. Actually, it is coming. Maybe the proof should be related with L functions of these elliptic curves. But I think one have to first. I should find out which classes is this. It was, I remember from some parts. If I find something interesting, I'll just write you.
Yes, please. So so usually I work with the high rank. I work, but in fact, I almost mentioned one problem. Then I choose it. I decided to have only one problem from this section, but I find also one interesting problem in, let's say, a smaller rank direction, namely the question. Is it possible to have rank 0 coming from Diophantine triples? And this is, so usually I didn't discuss much this question whether elements are positive or mixed signs, because in most cases the answer is the same. So one finds solution with mixed signs, and then with little work found solution with all positive elements. But in this particular case, the situation is quite different. So it is easy to find curves with mixed signs, meaning there are positive and negative elements in triple producing rank 0. But it is very hard, at least for me, to find example with positive elements producing rank 0. And in fact, I have only one example. In joint work with and Mikic, we found only one example, huge example. This is perhaps why I didn't put it on slides, because I should use some small fonts to fit this example here. So we have one example of triple, Diophantine triple, rational Diophantine triple producing rank 0. And question is whether there are other examples, whether there are infinitely many examples. So there is no obvious obstruction, but we are not able to find other examples.
Okay, thank you. Are there more questions or remarks? You have
Neyse
some
arkadaşlar hazırlanın da çıkalım.
there are some thank you messages on chat. And I have some small announcement. In February, we have one more talk for winter semester. And our next speaker will be Luis Diolla from University of Barcelona. So thank you very much for the speaker again for this interesting talk. And see you in the next seminar.
Thank you so much for attending my talk.
It's my pleasure. It's our pleasure. Okay, bye-bye.
Bye-bye.